Good weekend, everybody? No? I'm sorry, I had it over the break. It's terrible. I'm surprised to see you here today.
Yeah, I didn't find out till yesterday, so.
Yeah? Alright. Hey y'all, we have an exam a week from today. It'll cover chapters 0, 1, and 2, right? Not chapter 3, though we might get a little bit into chapter 3. It won't be on the exam. We will have a quiz too on Thursday, okay? Let's just go and do a quiz just on chapter 2. It'll help you prepare for the exam. What's that? Yeah, reading quiz on Thursday and an exam on Tuesday. Chapters 0, 1, and 2. Yeah.
I'm gonna rest. Chapter 2 are all.
Let's do the whole thing.
Alright.
Right? And we'll have finished all of it, I think, by then. We'll probably wrap it up today. And then we will likely move on into chapter 3. We'll probably have plenty of time to move on into chapter 3. But not on the exam. We'll say chapter 3. Okay? Format of the exam is roughly 50 questions, multiple choice. You know, we have an hour 20 to take it, but students don't usually take that long. It usually takes no more than an hour. Some students half hour. If you know it, you know it. If you don't. It'll be a lot like the reading quizzes. It'll be a lot like the exams that you find online, so use those for practice. But please do know that while the reading quizzes, I'll often just take those questions from old exams, that for the test, most of the questions, sometimes all the questions, are completely new questions. They're similar. I mean, if you look at my old exams, you'll see that they're different, but they're still covering the same content. So those old exams are a great way for you to practice. Reading the book, reading the notes, those are all good ways to practice. The notes are a great way. The book sort of explains things in more detail. If there's a lot more detail in the book than in the notes, or if there's a topic that I don't discuss in the notes, then that won't be on the exam. Okay, but there aren't many of those, and usually I tell you outright, I'm not even sure that we've had any yet that are topics in the book but not covered in class. So the notes are a good guide for you to study. All that material will be on the test. And I generally cover all the material. I don't pick from sections. You know, I generally pull questions from all the different topics. Any questions about the format of the exam? What to expect? How to prepare? You should be preparing now. Getting ready. You don't want to wait till the night before. There's a lot of material to assimilate. You're not really going to get it all the night before. Okay? All right. Yep. We'll be getting ready for the quiz. We will have assigned seating, so we'll be spread out in this room, and there'll be a seating chart at the door for you to find what seat you're in. All right. Let's see. Where did we leave off last time? Oh yeah, we were talking about viscosity. Viscosity describes how thick a fluid is. Right, when we talked about maple syrup versus water, that maple syrup is more viscous, or pitch, like the pitch drop experiment, that's definitely a lot more viscous. Though we wouldn't usually think of that as a liquid, because it doesn't flow in the way that we think of liquids flowing. But different materials have different viscosities. There are some things that affect viscosity. Temperature affects viscosity. And usually, cold is more viscous. That sort of makes sense, right? The molecules, they just sort of become stickier to one another when they're colder. The viscosity affects the flow rate. And remember, flow rate, which we're calling Q, is a measure of delta V over T. It's a change in volume, how much volume of liquid goes past a point in a given amount of time. So it's in units of cubic meters per second, or cubic centimeters per second. Viscous fluids like blood need a constant pressure to make them flow. But non-viscous fluids do not need a pressure. Superfluids have no viscosity, and they will move through a barrier with no interaction. This, by the way, is not in your book, I'm pretty sure. There's no viscosity between the atoms of the superfluid and the atoms of the barrier. Again, not in your book. I want you to watch a little video. That's the only reason I include it here, because it's kind of interesting. And when you have these superfluids, which are cooled to very, very low temperatures, like darn near absolute zero. You know what absolute zero is, that temperature? We'll talk about it later. Absolute zero is the temperature at which all atoms stop moving. It's theoretically the lowest temperature that you can reach. We'll see that in a later chapter when we see heat and energy. But when you reach near that temperature, some fluids become superfluids, and they basically just don't interact with anything anymore. So if you have them in a container, they'll just sort of fall right through the container. It's like the container is not even there. Let's see, I have a video. Give me just a second. I think next time you go to McDonald's or wherever and you get, a Newton burger, right? The quarter pounder with cheese, you get a Newton burger with cheese, and then you ask for some superfluid in a cup, and then they're like, what? They're like, oh wait, the cup can't hold the superfluid. And then see what they say. Because it has no viscosity. No, you don't think you'll do that. Yeah, they'd probably spit on your hamburger. All right, let's try these clicker tests, these questions. We'll do the one on the left first. All right, we'll stop at 25. Okay, good. A is right. Remember, our flow rate is volume over time. And that's going to be cubic meters, length times width times height. That's cubic meters over seconds. That's our SI unit. It could also be cubic centimeters per time, but we'll go with A. And then let's look at this one. This has to do with our equation of continuity, which says that our flow rate has to remain constant. Just to remind you that Q1 is equal to Q2, and then we said that A1 V1 is equal to A2 V2. It's called the equation of continuity, and it follows from this. The flow rate has to always be constant, assuming you're not losing or gaining any liquid. So it leads us to that. All right, doing really well. Ask your neighbors if you're not sure. We'll stop at 48. 48. Okay, C is right. Some of you put A. I understand that that's sort of, if you decrease the area, then you think, well, maybe you decrease the speed too. But remember our hose, because that's effectively what you're doing with a hose, is you're decreasing the area when you put your finger over the end. And if I have an area A here and an area A over 2, when I decrease the area, I speed up the flow of fluid, because I have a smaller pipe here. In order to get the same flow rate through that smaller pipe, the liquid has to go through faster in order to move the same amount of fluid in the same amount of time. And then I can think about this equation. If I decrease A2 by a factor of 1/2, then that means that I have to increase V2 by a factor of 2 in order to make these two sides still equal to one another. And so a lot in this class, that's what you'll be doing when you're looking at these mathematical relationships, and you'll be comparing one side to the other. And in this case, I know that the left-hand side is remaining constant, but I'm decreasing the area from A1 to A2 by a factor of 1/2. when I do that, I increase the speed by a factor of 2. Okay? You will see questions like that on the test, probably on the reading quiz too on Thursday. Yes, we okay with that? Can do that on the test for me? You guess? All right. Practice, practice, practice. That's what's going to help you, okay? If you practice the old test, read through the books, that will help you to be able to do this. You are capable of doing it. It just takes practice. It sort of seems foreign right now. All right. When the heart contracts, blood flows from one region to another, causes a distinctive sound. What type of flow is that? Is that sound caused by? Okay, doing really great. I think now everybody has the right answer. If you ask anybody in the class, they'll tell you what you mean. Oh, yeah. Just a few more seconds. We'll stop at 34. Okay, awesome. C is right. That's turbulent flow. When the heart contracts, all the blood inside your heart just starts moving. It's all jumbled up, and that's turbulent flow, and it caused a specific type of sound. And why can you not hear pterodactyls go to the bathroom? Because the P is silent. This pterodactyl starts with a P. Did you know that? It does. It starts with a P. Which of these is not a characteristic of ideal fluid flow? We had 4 properties of fluid flow that makes that flow ideal, which is mainly what we're dealing with. Which of these is not a characteristic? Awesome. All right, let's stop at 33. 33. Awesome. E is right. All of these are characteristics. It needs to be laminar. It needs to be rotational. What's the opposite of laminar? Turbulent, right? The opposite of irrotational is rotational. That means it's rotating. Steady. I think it was just like non-steady, right? Yeah, non-steady. And then non-viscous, the opposite of that is viscous. So anything not those is going to be not ideal fluid flow. All right. We will see with the flow of blood, which is not really ideal fluid flow because blood is not non-viscous. It is a viscous fluid, that we can use an equation called the Poiseuille equation that describes how different variables affect the flow rate. And we'll see that the viscosity is one of those. Also the pressure. Remember, with a viscous fluid that you need a constant pressure differential, a constant source of pressure to push that fluid through the pipe. The Poiseuille equation looks like this. It is pi r to the 4th times delta P divided by 8 eta. That's the Greek letter eta. It sort of looks like an N, but with a script on the end, times L. You're not going to have to calculate anything with this, but I do want you to know the relationships. Like if I change one of these variables, how does that affect the flow rate? For example, if I change the pressure differential, if I change the radius of the vessel, if I change the viscosity or the length. These different variables. R is the radius of my pipe. Pi, of course, is just pi. If I have fluid flowing in this way, I have one pressure on this end and one pressure on this end, and delta P is going to be the difference in those pressures, P2 minus P1. Right, where this would be my low pressure, or excuse me, no. This would be my high pressure, and then this will be my low pressure. The length is L. It's just the length of your vessel, your pipe, or whatever it is that you're dealing with. I think that's all. So R is the radius. Delta P is the pressure difference. That should be a capital P, by the way, not a lowercase p. Eta, E-T-A, it's the Greek letter eta. It is the viscosity. So if eta goes up, it has more viscosity. So, I asked you which is more viscous, pancake syrup or water, and everybody knows it's pancake syrup. But I could also ask you which has a higher value of eta. And so you need to know that eta refers to the viscosity. And then L is the length. All right? So if you change these variables, I need you to know what's going to happen. I give you this equation. It's on your equation sheet. I think that's right. Let me double check. Yeah, I give you this equation, so don't bother memorizing it, and don't think that you're going to have to calculate it with numbers. But I want you to know what happens when you change these variables. So for example, there is a linear relationship between Q and P. So if P goes up, that means Q will increase. That sort of makes sense, right? In fact, all of these are sort of intuitive, that if P increases the pressure differential, then I'm going to get a higher flow rate. There's an inverse relationship between Q and L. So if L goes up, that means that Q will decrease by the same amount. So for example, let me write my equation over here. Q is equal to pi r to the fourth delta P divided by 8. That's not right. 8 eta L. If I increase this by a factor of 2, then I decrease that by a factor of a half. Okay? It's an inverse linear relationship. And then Q is also inversely proportional to eta. So if eta goes up, if the viscosity goes up, that means that the flow rate will go down. It won't move as quickly. And then there's this radius dependence. And there's a very strong dependence on the radius because we have this r to the fourth. So Q is proportional to r to the fourth. So, for example, if r doubles, what's going to happen to Q? If R doubles, what's going to happen to Q? Will Q double? Will I get twice Q? Will I get 4 times Q? 8 times Q? 16 times Q? Which of those will I get? If I double R, I make the radius of my pipe twice as big, but I keep everything else the same. The pressure, the length, the viscosity, and I assume that the pipe is fully filled, that I have enough fluid just to push it in and fill up the pipe. What's going to happen to my flow rate? If I double R, what's going to happen to Q? I double this variable, what happens to Q? Is it double, quadruple, times 8, or 16? All right, I'm going to leave it up and let you check your answers. I'm going to give you a little help here. So let's get rid of this. If I double R, if I put a factor of 2 right there, then that factor of 2 is going to carry through with this fourth power. And so really what I'm asking is, if I double R, then that means that this this Q over here is going to increase by a factor of 2 to the 4th power. Now we saw this with quadratic relationships, that when I have something that's, say, proportional to, say, r squared, if I doubled r, then I would get a factor of 4 increase on the other side. But here I have a 4th power. And so we want to know what is 2 to the 4th power. A lot of you had A, by the way. Not so much anymore, but a lot of you had A, and A is not right. That if I double R, it doesn't just double Q. It does a lot more than that, because Q is greatly dependent upon R. All right, let's stop here in just a second. I'll stop at 158. Very good. So D is the right answer, because 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 to the 4th equals 16. So a big, big dependence on R. If I make R bigger, or if I make R smaller, then it's going to greatly affect my flow rate. Okay? I talked about that, but I'll still give you a choice. Where does a one-legged lady work? Don't give away that. Who did that? IHOP. Yeah. She said IHOP. Oh, that's another joke?
Another one-legged lady.
Yeah, I have another one-legged lady. That was it. But I can't use it now. Oh, what's the name of a one-legged lady? Eileen. So one day, I'm actually going to have a one-legged lady in my class. I'm not going to be able to use those jokes. Maybe one of y'all have one of them? I don't think so. Are they insensitive, those jokes? The one-legged lady jokes? She might have a sense of humor. All right. I think if you have one leg, you just sort of have to face life with a sense of humor. That's it for the physics section. By the way, you're going to see questions like this where I ask you what happens to this variable if this variable changes. And you'll go through your equation sheet and sort of look at the different equations and ask yourself those questions. If you're not sure on how to do it, by all means, come see me. We can sit down and probably 5-10 minutes. I'll have you being a pro at this. Okay? You want to look at, is it in the numerator or is it in the denominator? If I change something in the numerator, it's going to increase the thing on the other side. If I change something in the denominator, if I make it bigger, it's going to decrease the opposite side. Okay? And then you want to look at to see, is it squared, cubed, to the 4th power right here. And if that's the case, then you have to multiply that factor by itself however many times in order to see what it's going to do to the other variables on the other side. Okay? All right. Let's look at the circulatory system. Circulatory is 2 parts. Y'all know the different circuits, right, in the circulatory system? That's right, the systemic and the pulmonary circuit. The systemic circuit takes blood to the body. And the pulmonary circuit takes used blood to the lungs for replenishment. That's what pulmonary means, right? That it's like the lungs. Takes used blood to the lungs for replenishment. And so it's obviously much, much shorter. The systemic circuit starts at your heart and then it goes all throughout your body. But the pulmonary circuit just goes from here to here, from your heart to your lungs. We'll consider this system to be closed. It's not exactly closed, right? The circulatory system, but we'll consider it to be closed. So there's nothing coming in, nothing going out. So the flow rate is constant. And if I say that the flow rate is constant, what that means is that Q1 is equal to Q2. That Q is equal at the heart and it's equal at your pinky toe. That the flow rate is always going to be the same. And so the continuity equation, A1V1, is equal to A2V2. And since blood is viscous, the Poiseuille equation also applies. And then for viscous fluids, you need a continual drop in pressure. I do want you to know the parts of the heart. You don't need to know all the valves and stuff, but I want you to know the order of blood flow after it leaves the heart and then returning to the heart. And then I want you to know just the names of the 4 chambers of the heart and be able to identify them, either in a cartoon figure or in an actual picture of the heart, or in an actual heart that I might bring to class. No, I'm not going to bring a heart to class. Wouldn't that be cool? Yeah. We have a cow heart upstairs, but they don't really let me. Oh, yeah. They use it for their biochem class. They do something. They culture cells or something. Have you had biochemistry? No. Okay. So after leaving the heart, we go from the aorta to the arteries. These are getting smaller each time. To the arterioles, to the capillaries. Spell that right? Yes. To the capillaries. And then when you return to the heart, coming back from the capillaries, you go to the venules, the veins, and the vena cava. What's that? Is it your favorite organ? Really? I don't really like the heart like that. It's okay. I mean, I'm glad to have one, but otherwise. I want you to know the 4 chambers in the heart. So this is just a little cartoon version, though we'll see like a more detailed version later. But this is the right side, this is the left side, because, you know, it's like stage left, stage right. Right? So if I'm looking at myself, my left side of the heart's on the left side, right side's on the right side. So I'm looking at it here, it's like stage right, stage right. Is that a good way to think about it? No. Yeah, it's just opposite. So like, if I'm standing here, this is the left side of my heart, this is the right side of my heart. And then the atrium is the top, and I always think about in a hotel. That's these parts right here. I always think of, you know, you have in a hotel, you ever see, you know what I'm talking about when I say atrium in a hotel? Like you go into a hotel and you have the big glass roof, that's the atrium, sort of. And so it's up top. And then the ventricles are in the bottom. What's that? Yeah, I don't know. How do y'all remember the ventricles? Not the atrium. That's what I remember too. Not the atrium. Okay? So I'll likely give you a version like this, and you just have to identify A, B, C, D, what is what. Blood flows out of the left ventricle. Through the aorta. Goes through the systemic circuit. And then it returns. It's going to be depleted now, right? Because all the oxygen and whatever, the nutrients have been taken out of it. And depleted, it returns to the right atrium. Then it goes to the right ventricle. Through the pulmonary artery. to the lungs, and it returns to the left atrium. Through the pulmonary vein. All right. Your book talks about this in more detail, but you do need to have an understanding of the flow that blood takes through the heart. It's important for you guys to understand that. All right. Let's have another picture here. It shows the atrium and the ventricles. There are 4 one-way valves in the heart. You don't need to know those for the test. You don't need to know the names of the valves. But I do want you to know just the basic flow, including the 4 chambers and the major arteries and veins. I know some of you already know that, but if you haven't had that course, A&P, then just spend a little time thinking about that. Trying to memorize those different parts of the heart. Okay? It is important for you to know. 4 one-way valves. Don't need to know for me, but you might need to know it one day, right? All right, let's do some of these. Let's try this one here on the left. Let's see what you think the answer is here. What happens to the speed of the blood flowing through the blocked section? All right, we're doing the one on the left, the one here with the artery that's blocked. We're going to stop at 42, and then we'll do the one on the right. Okay, it is increases. This is an application. Do y'all remember which equation this is an application of? The what now? Yeah, the cross-sectional one, where you have the cross-sectional area. The AB equals AB. That's what you see. See? That's correct. So it's an application of the continuity equation. A1V1 equals A2V2. And what's happening, if this is A1, this is A2, that A2 has shown a decrease, so V2 is going to increase. That my speed will increase there. And now consider the Poiseuille equation as it relates to the systemic circuit. What happens then to your overall blood pressure if you get a blocked passage in your artery? What happens to your blood pressure? This is your overall blood pressure. We'll address sort of localized blood pressure in just a second. But what happens to delta P if R decreases? I'm going to go ahead and write the Poiseuille equation here. It's in your book. All right, let's stop at 50. Okay, good. A is right. If R decreases, that means that delta P is going to increase. So the systemic blood pressure, the overall blood pressure is going to increase. So some of you might say, well, what really happens in an artery when it gets blocked like that? Do y'all know what happens? What can eventually happen to the artery if it gets blocked? Not just rupture, something else. Okay, a heart attack. What's somebody? Yeah, that's not right. Yeah, those things are all. Huh? What? But it can collapse. That you can actually get arterial collapse if you get blockage. The whole thing will just collapse in on itself. But in order for it to collapse, what does that say about the pressure right here? If this thing just collapses in upon itself, what does it say about the pressure right here? Is the pressure big or small than the pressure on the outside in order for it to just collapse in upon itself? What do you think? How can I get it such that this thing will just smoosh down and close off completely? Yeah, the outside pressure is bigger than the inside pressure. And it's not that the outside pressure increases, but the pressure on the inside, the pressure of the blood inside the artery decreases. Now that's different from what we said over here, because this is talking about what is the overall pressure that causes this flow of blood to speed up. And you need because when R decreases, I have to get a higher pressure to make it speed up, to go through that blocked passage. Now this gets to something we call the Bernoulli Principle. Your book doesn't talk about this, but this is one thing that I do want you to know about. So the Bernoulli Principle, I don't think it talks about it, does it? The Bernoulli? I'm pretty sure it doesn't. The Bernoulli Principle is kind of complicated, but in short, one of the things that it concludes with is that if the speed of a fluid increases, the pressure of that fluid decreases. And the big application of this is in an airplane wing. If you've ever been in an airplane and wondered, how does this thing lift up off of the ground going, not really that fast? Well, what's the deal? Like, what's causing this thing to just lift up out of this into the sky? What you get is a wing that's shaped like this, that you have a curved section on top and a flat section on bottom. And it might not look exactly like this, but this is the basic idea. And then I get air that flows over the top and air that flows under the bottom of the wing. Now on the top part here, the air flows faster. As if you imagine two particles coming on here, they separate and then they come back and they meet here. And so this one travels a farther distance, and because it travels a farther distance, have these two particles, they separate and they come back. This one's traveling a farther distance, and then it's going to be traveling at a faster speed. So I have a high velocity fluid here and a low velocity fluid here. High velocity on top, low velocity on the bottom. So if the velocity goes up, that means I have a low pressure on the top and a high pressure on the bottom. That's what causes lift, that I have a pressure differential. High pressure on the the bottom, it's causing this thing to lift up. I showed you this on the sort of the first day of class when we went through a bunch of demos. But remember the little ping pong ball in a cup? That if I put a stream of high velocity air across the top of the cup, it creates an area of low or high pressure right here. Low or high pressure right here. High velocity, low pressure. Right, so if I do it I can, you'll see the ping pong ball? You'll see? Isn't that cool? You can just carry a ping pong ball with you all the time, and then if you ever have a class, you just put a ping pong ball. And show your friends that this Bernoulli's principle is going to play here. We showed you this for the hair dryer, my hair dryer from home. And the same thing happens here. I have this high velocity flow of air, and it's going to create low pressure surrounding the ball that will sort of act as like a pipe for the ball. You can move it over. Where it would normally fall off, but the air sort of holds it in place. The low pressure region around the hole. I know it's spinning. Check it out. All right. So that's the Bernoulli principle. You might have one question about it on the test, but it's not in your book. Okay. If the velocity goes up, the pressure goes down. And that's why when you get a blocked artery like this, the whole thing can just collapse down upon itself. But if it gets blocked too much, You know, it does cause your blood pressure, your systemic pressure to go up, but it will cause the local pressure, the pressure right here, to decrease, which can cause arterial collapse. All right, let's try the next one, the one on the left. The pulmonary circuit does what? Go back what? Sure. Let's stop at 40. Hey, look at you people. That's awesome. Which one was that? Oh, the pulmonary circuit. It takes blood from the heart to the lungs. The next question is, which side of the chicken has the most feathers? The left, right, what do you think? Front, back? Which side has the most feathers? You don't know? No, not that. The outside. Did you know that one? Yeah, it'll be on your test, eh? Which side has the most feathers? All right, and which of these is the rate of blood flow the greatest? The aorta, maybe? Venules? Capillaries? I don't know. Or is it the same all throughout the systemic circuit? All right, let's stop at 33, 34. You think it was the aorta, right? It's so big, so you gotta get a lot of blood through there. But it's gonna be, wait, no, did I put, yeah, D. That it's the same throughout all the systemic circuit. Right, because remember, we're thinking of this as a closed system, which it is effectively. And in a closed system, Q1, that's the blood flow at the aorta, is going to be equal to the blood flow at the capillaries. Now that doesn't seem right to you, right? Because the capillaries, the blood's just sort of trickling along through there, moving slowly. And so we'll talk about that on the next page about why that is, like why the capillaries appear to have such a slow-moving flow of blood compared to the aorta. It has to do with the cross-sectional area of the capillaries. As blood flows through the systemic circuit, it experiences a continual drop in pressure. If you remember when I first drew that figure, that pipe for the Poiseuille equation, so looking at P1 and P2, it's like P1 would be at the aorta, and P2 would be, the vena cava, the one that comes back. Vena cava? Yeah. So that's you have this continual drop in pressure. The highest pressure is in the aorta. That's like our P2 in that original figure. And our lowest is in the vena cava. You have to have that pressure differential in order to get that viscous fluid to flow through your whole body. All right, Poiseuille's law says that the pressure must be higher for longer systems. Remember, Q IR to the fourth, delta P over 8 beta L. So if L gets bigger, if L increases, if our system gets longer and longer, in order to have the same flow rate, I need a higher pressure differential. And so as a result, the pulmonary circuit is it shorter or longer, the pulmonary? Shorter, right? It's just like this long. It's a tiny little system. So the pulmonary circuit is much shorter than the systemic. So the pressure there should be considerably smaller. It should be less than it is. So just some pressures. Our systemic circuit is about 80 to 120 millimeters of what? Remember? Mercury, right? Hg. Where that's the height of the column of mercury that measures that pressure. So the pressure of the blood would push on a column of mercury, push it up 80 to 120 millimeters. So it's about that high, right? A pulmonary circuit is only 10 to 25 millimeters of mercury. I've never asked for those numbers, and I would expect to ask them on the test next week or on the reading quiz. But I do want you to know that the pressures are quite a bit different. And I just give you those as an illustration that you're looking at almost a factor of 10 difference between the pressure of the pulmonary and the systemic circuits, just because the length is so much different. We talked about gauge and absolute measurements. So blood pressure measurement is a gauge measurement. Remember, these are all related to one another. The absolute is equal to the gauge plus the atmospheric pressure. And for example, when we measure the pressure in our tires, we measure the gauge pressure. Because when our tire is flat, we don't say, oh, there's 100,000 pascals of pressure in our tire, which there is, right, the atmospheric pressure. But we're only concerned about the gauge pressure. And that's true for blood pressure as well. We have two numbers, like for example, 120 over 80, right? And the 120 is the pressure when the heart contracts. This is called our systolic pressure. And that's just the pressure when the heart contracts. Systolic, in fact, actually means contraction. So you'd expect that to be the bigger of the pressures because, you know, your heart is contracting and it's causing an increase in the pressure. And then the smaller number, the one on the bottom, the 80 or whatever it is when the heart relaxes. This is called diastolic pressure. Is the pressure when the heart relaxes, and diastolic means a drawing apart. A drawing apart. So when the heart pulls apart. We can apply Boyles Law. It's not really correct to apply Boyles Law because Boyles Law usually applies to gases, right? It's part of the ideal gas law. We can sort of think of it that if I increase the pressure, then that's going to change the volume, and that's true for the heart, but maybe not exactly the way that it is in Boyles Law. So Boyles Law is usually just for gases. But nonetheless, we're going to do an incorrect application of Boyles Law to the heart. Boyles Law, remember, said that PV is constant. That is Boyles Law. is part of the ideal gas law. The Boyles Law and Charles' Law combine to give you the ideal gas law. But Boyles' Law is when the heart contracts, that means that V goes down, the pressure will increase. All right, you need to understand just mathematically how to look at these types of relationships. When I have two variables that are on the same side of the equation, like right here, if one of them does something, the other has to do the opposite. So for example, here, if V goes down, that means in order to keep that value constant, then this has to go up. So for example, if I decreased V by a factor of 1/2, that means that the pressure would have to increase by a factor of 2. Okay? Anyway, the heart you can't really do this because the heart is dealing with incompressible fluids, and so it's a lot more complicated than how we would apply Boyles' Law. But it is true for the heart that when the heart contracts, the volume goes down and then the pressure will increase. So that's because you have blood flowing out of the system. But the pressure does increase nonetheless. And then also Pascal's principle. Just remember Pascal's principle. It's applied here that the heart applies a pressure at contraction. That is felt throughout the entire circuit, throughout the entire circulatory system. That was Pascal's principle. Remember Pascal's principle. I drew this piston, a container with a piston in it. And we say if we apply a force per unit area, a pressure here, that pressure is felt at every part of the system. Okay, and that's true for the circulatory system. The pressure that's applied at the heart is felt all the way throughout. That's why you can measure your heart. You can feel your heart right here, because the pressure applied here is felt all the way throughout the circulatory system. Okay? That this originates from the heart. Let's see. I think I have a video I want to show you. Yeah, we'll watch the video and then I have a few quick test questions. Which of these is greater, the systolic, the diastolic, or are they both the same pressure? Oh, thank you. Systolic, diastolic are both the same. All right, let's stop at 15. A is right. Very good. Two cats are on a roof. Which one is going to slide off first? And you say what? You say, I don't know. The one with the smaller mu. That's the frictional force, like the coefficient of static friction. And if it has the smaller mu, that means it has less friction. It's going to fall off the roof. That could be on the test, actually, because we did talk about friction. Let's see. Let's do the one on the right here according to the flow equation. Doing this one right here. This one was A, it's systolic. what happens to the speed as area decreases? If I decrease the area, the cross-sectional area of my pipe, what happens to the speed? All right, let's stop at 35. 35. Awesome. A is right. V will increase. Flow equation says A1 V1 is constant, or is equal to A2 V2. And if the area decreases, that means my speed has to increase. This is all based on the fact that Q is a constant value in a closed system. And that's always true. If you have a closed system, the flow rate will always remain the same. What did the dog say after a long day of work? Roof. All right, let's try which of these phenomena cause the distinct sound while measuring diastolic pressure. Remember diastolic means a drawing apart. That is the lower of the two pressures. All right, let's stop at 32. 32. Oh, let's see what is the answer. B is right. Laminar flow is when the fluid is just sort of flowing along normally without interacting with the different layers. That is a property of ideal fluid flow. But when you're measuring diastolic pressure, that's when everything sort of goes crazy in the heart. And you get all this turbulence as it draws apart, draws in new blood into the heart, and you get all this motion, and that's turbulence that causes that sound. So B is the right answer here. And then for an IV, where should you insert it? Should you insert it in the vein or in the artery? And then think about why. Oh, okay. Let's stop at 30. A is right. Y'all know why? Yes, y'all right. It's a lower pressure. Did y'all know that? Did you just know it? Or you know it from reading the book? It was in the book. Did y'all know it before? Oh, okay. Yeah, so you put it in the vein because, you know, the vein is at the end, towards the end of the circulatory system. So that pressure differential, the highest pressure is right before it goes into the systemic circuit, and then the lowest pressure is right before it comes back. And so in the vein, when you're on the latter half of that circuit, that's where you're going to have a lower pressure. So the answer is A, vein. And the reason why is because you have a lower pressure in the vein. And it's just easier to get the medicine to go into the vein than it would be in the artery. You'd have to actually apply a pressure to the medicine to get it to go in. Let's see. Oh, y'all like this one. How do you count cows? Count cows. You know, moo. How do you count cows? With a calculator. All right. I don't think y'all do very well if the test was these questions. Like if there are these questions right here, y'all do just fine. But if it's the calculator questions, bad. You do bad. You don't need a calculator. All right. All right. Oh, this isn't. Clicker. So what happens to the speed of the blood as it moves from the aorta or the capillaries? Does it increase, decrease, or stay the same? What does it do when it moves into the capillaries? Does it move faster or slower in the capillaries? It moves a lot slower, right? Your book gives the different speeds, and it's quite a lot slower. So as it moves from the aorta to the capillaries, it is going to decrease a lot. But that doesn't seem to seem right because I know that A1 V1 is equal to A2 V2. And in order for V to decrease, which is what we're saying, that means that the area has to increase. But that doesn't seem right because the capillaries are itty-bitty compared to the aorta. I mean, I can stick my pinky finger into the aorta, but your capillaries are minuscule in comparison. But of course, the difference is that I have one artery, but I have many, many, many capillaries. So the combined cross-sectional area of the capillaries is actually bigger than the area of the artery. The combined area is bigger than the artery. So that's why I get a lower speed of blood through the capillaries, just because there are so many more of them, and when I add up all their cross-sectional areas, their total cross-sectional area is bigger than that of the artery. As the blood flows from the aorta to the capillaries, the pressure differential drops. Then what would happen to the flow rate if the pressure differential drops? Hold on. No, we're going to skip this. I don't like this. Sorry, I meant to take this out. So we're just going to skip this altogether. Just forget that it's evening. Just put a big X to it. And I think we'll probably skip the IV stuff too. The book goes through this about how to calculate the how to administer this medication, like how to what do I want to do? Oh, how to determine the height of the bag. Like in nursing school, you ought to do that, right? But you have to calculate the medication. But we're not going to do this page, I don't think, at all. Yeah, we can do squeezing the bag. Let's just skip down to here. Yeah, you can X out here. I'm sorry, I meant to take it out and up. But when you have an IV bag, squeezing the bag increases the flow rate. I mean, now you have machines that do it, but if you have just a bag, you can squeeze it, and that increases the flow rate. What principle or law is that an application of? Pascal's, Boyles, the ideal gas law, or Charles's law? All right, let's stop at 42. 42. Oh, I'm sorry, I hope you got in.
Yeah, I did.
Okay, good. Okay, A is the right answer here. So Pascal's principle, because when I apply a pressure to that bag, that pressure is felt all throughout that incompressible fluid, and then that pressure is transferred down to wherever the needle is going in. It causes a bigger pressure differential, which causes it to feel like that. You can identify all of these. Pascal's has to do with pressure being transmitted equally in an incompressible fluid. Boyles Law has to do with our pressure and volume, like when we inhale and exhale. I remember, as I said, that I will allow you to breathe in the exam. So that's sort of like cheating a little bit, breathing, because it's a good demonstration of Boyles Law. And then the ideal gas law is the PV equals nRT. And then Charles' law, we never wrote that down, but it has to do with the relationship between T and P, I think. That's the other part of the ideal gas law. Okay, this is PV. This is PV equal nRT. Okay, coronary arteries, the book talks about this. Arteries can be blocked with cholesterol. And changing the radius of the artery affects the blood flow. Can I tell you an interesting story? Don't write this down. But one of our alumni, he studies cardiovascular disease at University of Texas. He has a PhD, he's a research scientist there. And he does sort of basic level research in studying cardiovascular disease and how to cure it. And so what he's doing is he works with mice. And he came this past semester and talked about it, that's how I know. But he told us that mice are actually very healthy. Like, it's very difficult to get a mouse to get cardiovascular disease. They feed them all this extra stuff, just really unhealthy diets, and try to make them get cardiovascular disease, but it's very, very difficult to do. Their arteries are they're really clear and clean, no matter what you feed them. And so what they have to do in their research lab, and you might think this is, huh? No. They have to go in with a little wire, like a little metal wire. They cut open the poor little mouse. It's still alive. They cut it open, and they take a wire, and they scrape the inside of their arteries to cause inflammation. And then that mimics cardiovascular disease. And then they stitch them back up again, and then they eventually die from whatever cardiovascular disease. But isn't that interesting? Did you know that mice were so healthy? Huh? Well, he's working to cure, hundreds of thousands of people, millions of people over generations. So maybe we can lose one little mouse, or probably more than one. But did you know that mice were so healthy? So next time you have your mouse, just give them some cheese. It doesn't really matter. Even the really big mice, their circuits were just awesome. Their circulatory systems were awesome. All right, so changing the radius of the artery, like with cholesterol, for example, that blocks the artery, can affect the blood flow. Again, the Poisson equation, pi r to the fourth, delta p, over 8 eta L. If r goes down, then delta p goes up. And we saw that. And remember, this is the overall blood pressure. Sort of like the systemic blood pressure, what you measure with a cuff on your arm. But if we're looking at an artery that's blocked like this, by the Bernoulli equation, if V goes up, which it does, that means that the local pressure, the pressure right here, will go down. Okay, so we're saying two different things here. That if the radius goes down, the pressure goes up. And then I'm also saying if the radius goes down, the pressure goes down. Two different things, but they're different kinds of pressure. One is the systemic pressure, the overall pressure of the blood in your body, and then the other is the localized pressure right at that location. And that can cause your artery to collapse if it gets too bad. If the speed gets too high and the pressure gets too low, the whole thing will collapse in upon itself just from the outside forces. All right, let's do the one on the left here. The one on the left, decrease in the radius. There's a few more seconds. We'll stop at 31. Awesome. A is right. A decrease in the radius will cause it to increase. So, for example, a decrease in the radius of, say, a half will cause an increase in the pressure by a factor of 16. Right? We saw that before. That if my radius gets too small, as my radius gets small, my pressure increases by a factor of the radius to the fourth. Okay? With me on this? Okay. Good. Decrease. Oh, well, let's not do the percentage. We'll just put an X through that. So I need to go back and revise this chapter. An arterial collapse. We've talked about this. Bernoulli Principle is at play here. If V goes up, that means P decreases, and that's like in our clogged artery, where I have a small velocity here and a big velocity here. It's like putting your finger over the end of the hose. It has to speed up. And when that happens, I get a low pressure. Alrighty? What do we got here? 1035? Is that right? 1020? No! Like, that joke never gets old, does it? Alright, we'll stop there. Don't ever say I didn't let you out early, because I'm doing it right now.